So here we go with the recording, and welcome to class.
Okay, well, welcome everyone. So I just, this is actually Alfredo's lecture today, but I just wanted, since this is our first session, I wanted to just take a few minutes to introduce the course a little bit. Alfredo will give you more details about the plan for the whole course and the mechanics of it, and a lot of issues of tools and software and things like this, and we'll clarify things that I explained during the course that you may not understand directly during the lecture, but Alfredo will make everything clear. I thought I would talk a little bit about the history of this, right? Because this is not something that we talk very much about during lectures, and deep learning really is the descendant of work on neural nets, which itself is the descendant of work where people try to understand how biological systems kind of organize themselves, particularly self-themselves. So going back to the 1940s, two gentlemen on the right, McCulloch and Pitts, came up with the idea that if you connect very simple computing elements that are essentially what we now call McCulloch and Pitts neurons, binary neurons, you can do logical operations. And if you can do logical operations, you can do reasoning. And so they had this hypothesis that essentially the brain was a very large, this is not a hypothesis, this is a fact, the brain is a very large network of neurons. And those neurons are actually somewhat binary in the brain. They either turn on with a spike or they turn off. And so they say if you have binary elements, you can compute, you can do logical calculus. You can do inference, logical computation, and perhaps this is a process that the human brain uses for reasoning and perhaps the brain in animals. So very soon, so simultaneously, Donald Hebb, who is a psychologist, came up with a proposal for how neurons in the brain by changing the strength of the connections between neurons can sort of change their function, if you want. And so it was known in neuroscience, but the idea that learning proceeds by changing the strength of the connection between neurons is this idea. And Hebb proposed that if two neurons are active at the same time, then the connection, the synapse that connects them strengthens. And if they're not active at the same time, then it kind of gets depressed. So this is called Hebbian learning. And this was sort of a general idea that a few people kind of reused in the first sort of artificial neural network models. There's a lot of work that I'm not mentioning here, but in the 1940s as well, Norbert Wiener founded a field, a discipline called cybernetics. We don't use that word very much anymore, but we call this now system theory or things like this. There's a lot of subfield of cybernetics now, but we don't very much use that word anymore. But it's the idea that when you have sort of complex systems in interaction with feedback, you can have sort of very complex phenomena emerging, and so he came up with sort of a bit of general theory for this, and out of that came thoughts about self-organization or auto-organization, if you want to be Latin. And this is the idea that if you connect lots and lots of very simple elements with a very simple rule to kind of make them compute, they perhaps might be able to self-organize themselves into having a sort of emergent property. And this is something that we observe with biology and with the brain in particular. The elementary components of the brain are very simple conceptually, but it's their connection, it's their network that gives emergence to things like intelligence. So that was a very mysterious process back then. Then in the late 50s, Frank Rosenblatt, who also was a psychologist actually, came up with a system called the perceptron, an idea. So it's a very simple idea, which is the basis of what we now call supervised learning, of basically having a system that can learn to, for example, classify patterns represented as a vector of numbers or activities, or voltages in this case, by adjusting weights, the weights being similar to the synapses of a neuron. And he was able to demonstrate that such systems that basically learn by error correction can learn basic things. This is what we now call the linear classifier, or which is an example of what's called statistical pattern recognition. So it's a very simple idea. You show an image to a system, you see if it gives you the right answer. If it gives you the right answer, you do nothing. If it gives you a wrong answer, you adjust the parameters, which are weights of a neuron, so that the answer gets closer to the one you want. And then you keep doing this with thousands of examples. They didn't have access to computers at the time. So what he did was that he built an analog machine, an electronic machine that basically implemented all this. And that was the physical perceptron. You see pictures of this at the bottom left. And in fact, one of those pictures is Rosenblatt holding a row of 8 weights. The weights were actually potentiometers with a motor, so they could rotate. So it's basically an electromechanical computer, if you want.
We made a replica somehow this past semester.
We made a replica, yes. Actually, Philip Schmidt, who's working in our lab, made a kind of a replica of this, but with modern technology, it's much easier. Then, almost simultaneously, Bernie Widrow at Stanford came up with a slightly different model called Adaline, which is very, very similar in many ways. Also a basic linear classifier. And around the same time, neuroscientists discovered some basic properties about the architecture of the visual cortex, which turned out to have a big impact several years later, which I'll come back to. So they actually got a Nobel Prize for this. So this was very well known. This became very well known, and they discovered that neurons in the visual cortex basically look at kind of a small area of the visual field, and many neurons at different places in the visual cortex basically perform the same operation. The third picture from the left is at the bottom is Hubel and Wiesel. Then there's some work on all of this in the 1960s. And then in 1969, Minsky and Papert from MIT published a book called Perceptron that actually pointed out the limits of the perceptron. And they said, trying to build intelligent machines from the basic idea of the perceptron is basically hopeless because of those mathematical limits. And so really, that's not the right way to go. We should pursue the idea of intelligent machines in some other way. Okay, and that basically killed the entire field. So people stopped working on these things in the late 70s. They didn't really stop working on it. They changed the name of what they were doing. But people in AI who are interested in sort of reproducing the process of intelligence, if you want, started working on things that are more based on logic and sort of more classical computer science. What was not then yet classical computer science, but what became kind of classical computer science. Algorithms, search, logic, things like that, reasoning, and sort of abandoning all the kind of the type of things we observe in animals. So this is, again, more pictures of the perceptron at the bottom. Now you can reproduce the 3 pictures at the bottom here with about, half a page of PyTorch. But back then it was kind of a major undertaking. And then on the right here is Bernie Widrow with the original Adaline, which was also an analog computer where the weights were electrochemical, actually. And the basic element in those were the Macaulay-Pitts neuron that performs a weighted sum of its inputs, where the weights are adaptive, and then compares it to a threshold and turns on if it's above the threshold, turns off if it's not. So a little bit more history of what happened afterwards. So basically, research on neural nets and this kind of stuff kind of pretty much died in the West, at least in the 1970s. There were so people kind of changed the name of what they were doing. That became known as statistical pattern recognition, and I'm missing an N here on pattern. Or for some others, Bernie Widrow, for example, renamed what he was doing as adaptive filters, and this turned out to have actually a huge impact on technology. Adaptive filters are used absolutely everywhere today, and for data communication, for every modem has an adaptive filter in it, for echo cancellation. So, for example, right now, if Alfredo talks, the sound comes out of my speakers and it goes back into my microphone. And if it wasn't for echo cancellation, you would hear his voice twice. But echo cancellation is basically an adaptive filter that learns to suppress things like that. So you can't have speakerphones without that. You can't have interactive video without that. But in Japan, research, which was kind of a slightly separate ecosystem for research, research continued in neural net. Kunihiko Fukushima came up with this thing called the cognitron and the neocognitron, which inspired a lot of people, including me. I kind of started getting interested in neural net just around the same time, around 1980. And I was really influenced by those papers. He got inspired by Hubel and Wiesel and tried to kind of have a sort of computer simulation, if you want, of the visual cortex according to the model of Hubel and Wiesel. He didn't have proper learning algorithms, so his system was a little brittle, but that was kind of a pretty heroic attempt. And then in the early 1980s, the physicists started getting interested in neural nets, and the physicists really didn't know the whole history of the perceptron, and so there was no kind of bad feeling about kind of working on neural nets like engineers and computer scientists had, who knew that the perceptron basically had been killed, and it was a bad idea to try to publish papers on this. Physicists didn't have those hesitations, and so Hupfield came up with a model which actually had been proposed earlier by other people, but he came up with a theory for it. It's a type of recurrent neural net that he showed could be used as associative memories. Again, other people had shown this before, Teuvo Kohonen in Finland and Nakano in Japan. But what he showed was that there was a mathematical analogy with systems that physicists were interested in, called spin glasses. And that got physicists interested in basically trying to use their methods from statistical physics to explain perhaps how the brain works. And one of them was Terry Sanofsky. He was actually a student with John Hupfield. From what he tells me, he's the one who actually got John Hupfield interested in neural nets. And he worked with Jeffrey Hinton on a model called the Boltzmann machine. I found, when I was working on this, I found this paper fascinating because this was really the first paper in my mind that allowed a system, a neural net, to be trained that had hidden units, right? So the main limitations of both Hupfield nets and Perceptron and Adeline and all the previous models was like they were basically single layer systems. Every unit is either an input or an output, and you only have weights between inputs and outputs. And really the limitation that Minsky and Papert showed, one of the limitations is that to really sort of have a powerful machine, you need multiple layers. Boltzmann machines were the first system, the first learning algorithm that basically allowed training with units that are neither inputs nor outputs. Do you have a question? Okay, no question. Then pretty soon, the idea of backpropagation came up, and it became practical to basically train multilayer neural nets with backpropagation. This required a major conceptual change, which was to switch from using binary neurons to basically continuous neurons, so that they were differentiable, essentially. And a lot of what we talk about during this class is really related to this idea of backpropagation. So that really was a watershed. It spurred a lot of interest in the field, and a lot of the community became fairly large. The NIPS conference, now called NeurIPS, kind of started around 1987. So this really kind of started the field of neural net, restarted the field of neural nets. A few years later, I proposed the idea of convolutional nets, which is basically inspired by the neocognitron and by Hubel and Wiesel, but it uses backpropagation for training, and that sort of allowed things like handwriting recognition and things like this, and more recently, image recognition. Then there's a number of progress that occurred, which may or may not be on everybody's radar, but they are important to me. Léon Bottou, who's now at Facebook, and Patrick Gallinari in Paris, proposed this idea that you could basically do automatic differentiation. You could build a neural net by assembling modules. And if you knew how to propagate gradient to those modules, you could basically compute gradients for any kind of a graph of interconnected modules. And Léon Bottou soon rejoined Bell Labs, where I was working. And we started implementing a software which were called SN at the time, that actually implemented this idea around 1992. And we used this for all of work. And it took a long time for the rest of the world to actually realize this was a very useful thing. So what you see in PyTorch today and TensorFlow and various other schemes are essentially derived from this idea, if you want.
And SN means?
SN means simulateur neuronal. So this was sort of the French name that we gave to our neural net simulator, if you want.
And the paper's in French.
Released in open source in 2002 under the name Lush. It's on SourceForge if you are interested. It's kind of a Lisp, it has a Lisp language at the front end. In the mid-90s, there was interesting work on recurrent net, like Hochreiter and Schmidhuber's long short-term memory and various other things. Interesting work also in speech and handwriting recognition on what's called structure prediction with neural nets, graph transformer nets, which we'll talk about a little bit in this class as well. And then nothing happened for about 10 years. People lost interest in neural nets. People in the machine learning community started being more interested in sort of simpler models that basically were single layer, and for reasons that are still mysterious to me. And nothing much happened. A few things. Yoshua Bengio came up with this idea of neural language model in 2003, which turned out to be really pioneering. There's a lot of work on this. If you have heard of GPT-3, this is basically the descendant of this, if you want. And a lot of models that use NLP today, the neural models for NLP are basically very inspired by either this or the last item here, the Colorbet and Weston self-supervised neural net for natural language processing. This is also a very pioneering paper, 10 years ahead or 15 years ahead of its time, of basically training a system to represent text by training it to discriminate good sequences of words from bad sequences of words where you have substituted some words by others, for example.
They won the 10-year award, right, on New Rips, I think.
They did, yes. Was that last year? 2 years ago, maybe?
2 years ago, I think. So it is, I think.
Because their original paper was actually earlier than 2010, but their journal paper, I think, was around 2010.
Yeah, okay.
But then in the mid-2000s, Yoshua Bengio, Jeff Hinton, and I kind of started a conspiracy to renew the interest of the community in neural nets. And out of this came out this idea that you can sort of pre-train a deep neural net, perhaps in a layer-wise fashion using autoencoder methods and things like that in a unsupervised or self-supervised manner. And that sort of restarted the interest of the community a little bit into neural nets, but only kind of a small community until around 2012, when it became clear that convolutional nets, when you run them on GPU and had large number of training samples, basically could beat every other technique that were around. So that was really a watershed moment. A lot of people became interested in deep learning around 2013 after this AlexNet won the competition. So this was from Jeff Hinton's group, Ales Krzyzewski, Ilya Sutskever, and Jeff Hinton. We also had been working at NYU on convolutional nets for various things, but we were not as fast to implement things on GPU. So our applications were good, but not as spectacular. And then 3 years later, Ilya Sutskever, who was working at Google at the time, he now kind of leads OpenAI research branch, showed that you can use neural nets, multilayer STM in this case, for neural machine translation and basically match the performance of traditional machine translation system. Simultaneously, people at Facebook AI Research, which was just the beginning of Facebook AI Research at the time, that just existed for a year, Weston Chopra and Board showed an idea called memory networks, which basically said, like, you can have modules in a neural net that are basically associative memories. A year later, Badano Kyung-Yoon Cho, who's a professor here at NYU, and Yoshua Bengio showed that you could replace this complex LSTM that Ilya Sutskever had shown by a relatively simpler architecture based on the mechanism of attention, where you have basically multiplicative interactions between weights that essentially gate can route kind of signals, if you want, in a complex neural networks. And when you combine the memory network idea with this idea of attention in sort of a big way, you build big neural nets with that, you get what's called a transformer architecture, which has basically completely taken over the field of natural language processing, and is now actually making inroads as well in computer vision. 2016 was ResNet, which was kind of a modification of convolutional net that really made a big difference, could allow convolutional net to be much deeper than they were before, and really sort of brought about a big progress. So there's a lot more here that is in the blank, more recent history, which you'll hear during the class. And the class will talk about the basic techniques, their sort of practical use, and how you can put them to practice. And I wouldn't say the theory, in the sense that we're not going to demonstrate prove theorems or anything like that, but certainly a lot of mathematical basis for all of this. The style is that in my lectures, I'm generally going to stay very sort of conceptual. I'm going to talk about things in sort of give you an intuition for how things work, and give you the grand ideas. Then the actual math behind it and the practice of actually making it work. A lot of this will be covered in the practicums, and also sort of in your own personal work. Okay, I'm going to stop here. And
hold on, there are questions for you.
Go ahead with the questions.
All right, so you covered like the historical part. What about the other edge? Like, what about the future, right? So what are the research you're working on? What do you think is going to be a good, direction?
Right. We'll talk about that also in the class. So towards the in the second half. So one big hot topic at the moment is something called self-supervised learning. So this is really kind of the descendant of this layer-wise unsupervised pre-training for deep network from 2006. It's kind of the same idea that, and also inspired by the Colbert-Weston system, and inspired by some work I did also in the 90s on what's called Siamese networks. So it's the idea that you pre-train a neural net not to perform a task in a supervised manner, but you pre-train it to just understand the data without training it for a particular task. And then you fine-tune it on the task that you're interested in. This has revolutionized natural language processing over the last 2 or 3 years. It's starting to revolutionize computer vision, and certainly a lot of areas where the amount of data that we have, labeled data, is limited. So self-supervised learning is really kind of the immediate future. This is what a lot of people are working on at the moment. It is making really quick progress. A lot of work is also being devoted to basically getting machines to reason. So a lot of what I've talked about here is basically perception, right? What we can do in neural nets is, perhaps what animals and humans can do in a very short time without thinking about it, right? So recognizing objects, navigating, things that don't require reasoning. But what about, if we want machines to be able to do long chains of reasoning or plan in advance or things like this, how do we need to kind of modify our architectures so that the machines are able to do this? There's a little bit of that going on in all the fields around transformers and things like that, but not a huge amount. Memory networks were really an attempt at sort of allowing machines to reason, access a working memory, reason on it, and then change the content of the working memory. So a lot of recent work on this. I don't think anybody has a complete answer for how you do this, but it's a big challenge to basically try to make reasoning compatible with deep learning, which means gradient-based learning, really. Classical methods for reasoning in AI are based on logic, and that's discrete and essentially incompatible with learning. So that's kind of a big challenge. There are other challenges which are a little outside of the reach of what we can do at the moment. So things like we know how to train a system to represent percepts like images and text and things like this. We don't know how to train a system to represent action plans in a hierarchical manner. And I think that's a major obstacle also. People are not really working on this at the moment because no one has any good idea of how to do it. But that's kind of a third challenge, I would say. So learning without labels, learning a little bit like humans and animals by observing the world, that's getting machines to be able to do this. That's a major challenge. That's what I'm working on. That's basically the only thing I'm interested in, really, research-wise. Getting machines to reason is a very interesting topic as well. A lot of people are working on this. And then the third topic is basically integrating all of this into sort of autonomous intelligent systems that has an objective, has a model of the world that allows you to predict the consequences of its actions, has a way of deriving a sequence of actions that will optimize its objective and allows you to learn all of this simultaneously. That would be kind of the ultimate intelligence system. We don't know how to put those things together yet. Those are the challenges. So have fun with.
Hold on, wait. Last question. And
sure.
So these were like interesting direction. What are the instead limitations? And what do you think about quantum computers, non-binary states? That's the last one.
Right. Okay. So I mean, current limitations are clear. When I talk about those topics of research, self-supervised learning, reasoning, etc. Basically, what I say now is that currently systems are not able to do this, right? With a few exceptions. One big challenge is, can we come up with learning paradigms that will allow machines to learn by observation and will allow them to acquire some level of common sense? No machine has common sense at the moment. All of AI systems usually has a very narrow intelligence. I'm kind of skeptical about sort of the applications of quantum computing to machine learning. It's an interesting field. There are people who are thinking about like the connection between machine learning, deep learning, and quantum computing, and whether one could be used for the other. It's still very much up in the air. It's not entirely clear. There's certainly not going to be any practical consequences in the short term, at least in the next decade. But as a academic research subject, it's interesting. Okay.
Nice.
All right. So have fun.
Thank you again for opening this semester and this year class. We'll see you on Wednesday, right? Same time,
Wednesday.
Same place. Well, there is a different Zoom link, but we all have the access to the calendar, so we know where to find you.
Okay.
Right. Thank you. Bye-bye.
Fun.
All right. So back to us. And yes, welcome again. And let's cover a little bit of following up topics, right? So one of the most interesting topics, for you, I think, is going to be figuring out how this course works, right? And so I shared with you already on the through the announcement. I shared the sort of rules of the class. You should already have access to that because, again, I guess you're here, so all of the people that are here right now have access, right? But more or less, you see that there are. So maybe we want to cover quickly the. Let me see. The grading part. That is what usually you're very interested. So I will respect that and. But okay, before talking about this stuff, right? So as you can see, this class is remote, right? And then. So it's going to be slightly different from how usually we held classes in person. Every interaction is going to be done through, a camera, a computer, and whatever. And so we still need to be able to communicate at the best of our capabilities, right? So as you have already noticed, what I'm trying to do is going to be like try to stop Jan as many times as I can, given that we have questions for him. Otherwise, he just keeps going and we don't understand. Well, we might lose focus and understanding of what's going on. So whenever there are like good questions, right? Not just... Whenever we actually have a proper question to ask Jan, we should be writing down on the chat, such that I understand what is the understanding and this the pace of the class, if it's too fast, too slow, whatever, and when we can interact, right? So interaction is the base to actually get something out of these classes, right? All these classes are recorded, right? I just press the record button, so eventually at the end of the class, you will be able to watch again this. Is the competition? I'm going to tell you in a sec. So see, all these lessons are recorded. Therefore, it means you can rewatch them later, right? this does not mean you don't come to class, right? The part that you come to class, it's I think one of the most important part, because you can get much more value out of being attentive during class and have this kind of interaction. I will try to have eye contact with you over there on the other side of the screen as much as I can. And again, I will be trying to be interactive for what I can, right? And these seem to be very effective whenever I've been using like the chat here, and by I ask to you, you write here, we somehow have a feedback loop, and we are managing to stay on the same page. But you don't have to turn on your camera, because again, otherwise, if everyone turns on the camera, you don't see anymore what's going on, I think. All right, so Jan's speed of talking was a bit faster. I know. You can watch the video recording and you can slow him down. It was just because he didn't want to steal too much time from the lab. But okay, this lab is like half gone through. So let's see what we can do. Will be the work with PyTorch. Yeah, of course. I'm gonna be talking about that right now. So yeah. So the point is that we should be able to learn, right? The point of coming to class is learning. And to be able to learn, you should be able to keep awake for the most of the class, right? If you go around and eat some ice cream because you're home and whatever, right? You may get distracted, then you don't get anymore back on track on whatever is happening. Yes, there are recordings, but again, recordings are just, you're sick one day. Yes, you don't miss out, right? So recording are like something you may use if you really, really cannot take a part of class, right? But otherwise, we should be able to, make like a happy group, happy interactive group. Also, I'm very sarcastic, okay? I'm just telling this in advance for whoever does not understand or know what sarcasm is. So what is written down in textual format is usually the official part. Whatever I say, take it with a pinch of salt, as in, I like to joke quite a bit. And so I will say funny things to make you smile and laugh. So don't get offended, please. Or like, if you think I'm a jerk, just let me know. You think that it's all good. I will try to be more cautious, right? Whenever I interact. Okay, so these are the main points. So yeah, the agreement is that I will, every time you don't understand something I say, right? Just ask me, what did you say? I didn't get it, right? So if you don't get something, at least in my classes, it's usually my fault. I'm not able to communicate with you, right? So my accent is bad. I haven't slept enough. That's usually very often the case whenever I'm overworked, or, something happens. There is, someone ringing the door, I'm at home, right? So someone will eventually bomb our lecture, like today, Jan, perhaps. But okay, that was somehow planned. Somehow it was not, since I don't even have his slides. But okay, it's fun, right? So life, it's interesting because it's different every day. Okay, so if you don't understand, ask me. I will repeat until you get it, right? So I'm positive that eventually you'll get everything I say, right? At least that's my hope, right? I will try my best. All right, first point done. Second point, how the grading and stuff works, right? That's the part that some of you are super interested. I have to be honest with you in advance, and I say I don't care. I don't care about the grade I'm going to be giving you. The grade is for you, right? To make GPA or things. I don't care. So I will not be mean, as in you get the grade that you want. I don't give you the grade I want. I don't care what grade I'm giving you. You should be the one responsible of getting the grade you want, right? And regardless of whatever the class goes, eventually you will get whatever you deserve, right? All right, so this is what your peers have done last year, actually. They were amazing. awesome too, right? So you will contribute as well if you want to make this website and course even a better thing. So this is the schedule from last year, and everything is recorded. As you can see, there is a video button here, and I spent, too many hours putting this stuff on YouTube. Anyway, so here you have all the video recordings from last year. And then here, history and motivation. You click here, and you have the summary of what Jan talked about today, more or less, right, from last year. So one easy way to get 3 points for your final score is going to be finding typos. If you find typos in these write-ups, you get 3 points, okay? I mean, yes, I'm slightly joking, slightly not. If you really help making open source, the course a better course, then you are rewarded. And everything is detailed in this document, right? So, right, that's the last year course, right? And you have also translations in, Arabic, Spanish, French, Italian, Japanese, and whatever. Because we want to be accessible, right, to everyone. Yes, you get an A with us. You can do research with us, okay? So if you want to join Jan's lab, get an A in this course. Then we can talk about joining the lab, right? But A is a prerequisite to be able to join. Do we use Python? Yes, we use Python and PyTorch for the coding part. Could we get access to the slide prior to the class? Yes, you will be able to. Whenever I know there are slides before class. Today, Jan bombed the class, so I didn't even know he had slides. Yes, usually you will have slides before. And all slides are online from last year. They're all online on the website, right? So, but I guess, yes, I will put the updated version as well if I know there are slides for a given day. Okay, so again, get an A. We can talk about joining Jan's lab. You have the class website. Okay, so I guess we have how much time? We have like 8 minutes before 10:30. Okay. Any material for books? And okay, I'm writing the book. The book is going to be out in December, so not yet. You don't need high skills in Python. You just need all you need to do the coding is going to be explained by me in this course. I never took a Kaggle competition, so you're not required to know what a Kaggle competition is. So we explain that as well. That's in a second half of the course. Okay. Last part. Okay, today we don't teach, I guess. It's fine. Administrative day, fine, cool. So again, since we are all remote, all digital, we are not interacting in person because there is this, pandemic going on, right? So how do I teach? Do I teach only in class? No, I also teach outside class. I'm very into teaching, right? And so if you're interested to get additional education free of charge, and everyone can access this stuff, you can also find much content on Twitter, right? So if you go on twitter.com and you go / you put Alf, and then you go C and Z, which is my surname, sort of shortening. If you go here, you're gonna see a lot of content if the website actually loads. Okay. So you're going to see a lot of content like this is whatever. This is like an advertisement. Leave it be. But otherwise, I usually post I post some food, but okay, never mind. Usually I post about machine learning and okay, there you go. So this is like math communication, right? So I try to push, my educational agenda online live, right? I'm into art and education, right? So in here, I was just talking about getting life organized. Okay, this is just the beginning of the year. Sorry, it's going to be a bit noisy, but usually, like you have like math content. For example, here I'll tell you about the latest new version book of Kevin Murphy, which was just released. This is a super nice book. But what I wanted to show you here was the first part, which you should really check out. It's going to be going on the search bar. you want to type something like from, and then you do colon alf c and z, and then you can write, for example, linear algebra, LA, right? And so if you write LA, no, maybe let's do linear algebra, right? Linear algebra. Okay, so here are very nice videos of linear algebra. This is fundamental, okay? If you don't know linear algebra, or if you're rusty in linear algebra, do check these videos out. This course is based on linear algebra. If you don't know linear algebra, then good luck in this field, right? No, not just with the course. I'm just talking about generally about the field. So this is really good. It's done by Gilbert Strang. Sorry, my bad. Yeah, William Gilbert Strang. He's just an amazing educator. He's old as, AF, but he's just amazing, right? So just check this stuff out if you don't know, if you haven't heard. Another stuff you want to see, okay, I'm talking about integral operators, you don't care. Another interesting part is this one, right? So this dude here, Grant Sanderson, is another person which is very into education. And he also makes free accessible content online, on this case in YouTube. And if you're really, really rusty in linear algebra, please binge watch this essence of linear algebra, okay? Everything I explain in my classes is based on this perspective, right? And so if you want to get started ahead, like how do you say, jumpstart your understanding of all the lectures, you may want to really binge eat these videos here. You can press the heart if you want. That's appreciated. And this is going to really help you for your class, score, career, future, everything, skin. Okay. All right. Jokes aside, check this stuff out. It's really good. Okay. I wouldn't be telling you this stuff. I don't get money out of these things. I'm just trying to be as helpful as I can. And we have 3 minutes left before the end of the class. Okay. All right. So enough advertisement. I just show you a cool video. Okay. And then next time we talk about PyTorch and things. Okay, so cool. This is appreciated, right? So your comments, I like your comments on the chat. So that makes me feel you are with me and I'm not too crazy. Okay. Okay. Again, if you think I am weird, that's okay. No, if you think I am a jerk, there you go. That's not good usually. So let me know privately, and I will try to be changing my something, right? But otherwise, this is me. I'm weird, funny, whatever. Okay, I'm very funny. Again, don't try private messages. I can't really reply to all private messages, right? Okay, so last bit, and this is going to be the end of the class. I'm going to be showing just a pretty video. In theory, today I should have shown what a neural network does, right? And usually when people talk about neural nets, the easiest thing to think about is classification. And whenever you want to do classification, when we have classification, basically it means try to sort, to split things, to sort things in different buckets, right? You have like pictures of a dog, pictures of a cat, pictures of a rabbit. You want to put each picture in the right bucket, right? And so what they show you usually are things like, okay, let's do this. Since we have the internet here, classification, right? So you want to use Google a lot, images, here. Okay, my internet connection sucks. No, classification. Okay, machine learning. What is this stuff? Okay, there you go. So usually, okay, this is what they do, right? That's what they show, right? It's a straight line. Okay, if it's a straight line, these two classes are called linearly separable, right? This is not usually the case. Usually what's the case is stuff is not linearly separable. Okay, let's see a picture. Okay. All right, there you go. Okay, this is better, right? So these points are not linearly separable, right? So you cannot write a straight line. And so people usually show that you can have these boundaries, which are called decision boundaries, which are like turning, right? So I don't like this perspective because it makes you believe that you can turn decision boundaries in weird way. What I like to do instead of having this representation, I want to warp the space such that that line is still a straight line, right? Because all we have in deep learning and whatever is going to be a linear decision boundary, right? This is my simple singular module. So when we have a neural net, which we don't know what it is right now, but I just show you now a very cute animation, you basically see how things that are not linearly separable, let's see, non-linearly separable data. There we go. So whenever you have non-linearly separable, like this one, you cannot separate them with a line. Or, okay, a better example. Okay, this one here, for example, you cannot put a line, right? They are warped. Let's say like a spiral, whatever, spiral. Here, so let's say you have a spiral, or this class is here. You cannot write a line through, right? You cannot cut them in half. So how do we get to classify a spiral? This looks exactly like my stuff. Okay. Oh, there we go. Here. So how do we get to write a line through this stuff? We're going to be using a network to move the space. And oh, there you go. So these are the intersection. See? Okay, this is me. So here you have a straight line, but then you cannot cut this stuff, right? And so I'm going to show you this video about how a neural network basically morphs the space such that it becomes linearly separable. And then we're going to say goodbye. So I don't take too much of your time, extra time. So let me open the video. This was a very interesting not planned class. And we go with this one. And we should be able to see something. So these were my original 5 branches, right? So these are not linearly separable because if you draw lines, you're going to be intersecting these classes, right? Instead, what the network does is going to be unwarp the spiral such that I can still draw lines, right? So I'm going to be showing here this animation. And next time I'm going to be explaining how everything is done, right? Just showing this for making you hungry, okay? Have you had breakfast? Yeah? I'm just kidding, like educationally hungry, right? What does morphing the space mean? Yes, next time I tell you everything. This is just to show you some very cool animation. This is the stuff I like, right? Also, my high schooler, here's a video, so you can find out if you write from Alfkant high school, you're gonna find my high schooler video on YouTube as well. So I'm really into this kind of visualization, education, and how do you call it? Not interpretative. What's it called? The thing you try to understand, right? You try to understand how it works inside. There we go. So this is basically what the network did. The network warped the space such that all the points now are spread apart. And then when these points are spread apart, they are spread apart in a specific way. This specific way is that they are now linearly separable, right? You can draw a line like this one between these yellow points and the green points. This bar is in the way. You can draw a line between the green points and the purple point, and so on, right? And what are these arrows? Okay, this is a question for you, right? For next time, let me know what these arrows are. There are 5 arrows in 2 dimensions. There are 5 classes. And we are on a 2D screen, okay? So let me know what you think next time, right? And this is a question for you to think about. And that was basically it. We are over time as usual. Sorry about that. I'm stopping the share screen. So all questions that are here that I didn't see, I will not be able to answer. Just write on CampusWire if there are, fundamental questions about the content. We will reply. There is office hours tomorrow from Jacen, super smart guy. Feedback on the class, anything. There is the CampusWire chat for the feedback. That's it. Okay, anything else? That's it. I think we are done, right? We are late. I'm late, but it's okay. I don't know if it's okay. I think it's okay. All right. Sweet. Next time, PyTorch. We're going to be looking into this stuff. I will write you down the architecture of this network, give you more context, and we'll get a little bit more meat, right? Like Jan took half of the class today, and then I couldn't finish. All right. Bye. And I cannot even close the thing.